Welcome. This session we will try to solve this continuous beam ABC using stiffness matrix method. Okay, the same problem in the previous video lecture we have solved the same problem by flexibility matrix method. Okay, right. Let us see how you solve this in a detailed manner. So first of all, you estimate what is kinematic indeterminacy of the given problem. Okay, so for this given continuous beam, what is kinematic indeterminacy value? Okay, this will decide your unknowns, your matrix size, your number of equilibrium equations, all those. Okay, so this is very crucial to decide what is the kinematic indeterminacy value. Okay, right. So just count the number of independent displacements present in the structure. So at A, no displacement is possible because it is fixed support. So 0. Okay. And at B, rotation is possible, horizontal movement is possible, but as this is a beam, horizontal displacement we are not going to consider. Okay, it is negligible, right? So it is neglected, hence theta b is possible. So displacement at B. Next, at C, rotation is possible, the same horizontal movement is possible, and as this is a beam, the axial deformations are neglected, so we don't consider that degree of freedom, right? So only rotation at C will be your degrees of freedom. So the value of Ki is 2, nothing but your degrees of freedom in the structure. Okay, right. Once you now calculate kinematic indeterminacy value, now assign the coordinates. Okay. So this is what we call generalized coordinate system in matrix methods that we follow. So I give theta b as coordinate 1, theta c as coordinate 2. Okay, right. So let us represent them in the form of a diagram. So here I give coordinate 1, and even the direction also you can see that clockwise is given as positive coordinate. Okay, so this is 1 and this is 2. So 1 refers to rotation at B, 2 refers to rotation at C. Okay, right. Now coming to formulation of equilibrium equations required for solving these unknowns. These are the unknown displacements in the structure theta b, theta c. So how you formulate equilibrium equations? Okay, right. So it is by writing delta matrix is equal to inverse of stiffness matrix, load matrix, total forces at the nodes chosen, and forces only due to the loads given on the structure. Okay, so this is the set of equilibrium equations represented in the form of matrices. Okay, as you know, Ki is 2, so all these matrix sizes are limited to size 2. Like this is 2 by 1 matrix, this is your 2 by 2 matrix, and same way this is 2 by 1, 2 by 1. So this is of 2 by 1 matrix. So likewise, as I said, kinematic indeterminacy will decide your number of equations required. Okay, right. So let us elaborate this one. So delta means our unknowns in the problem, theta b, theta c. Now K matrix, K11, 1, 2, 2, 1, 2, 2, inverse of this, and the corresponding load with respect to rotation is moment at B, moment at C, minus moment at B due to loads alone, moment at B due to moment at C due to loads alone. Okay, that is PL matrix. So once you arrive at these matrices, you can substitute and find what is theta B, theta C, the unknown displacements in the structure. Okay, now let us solve for, let's try to write first P matrix. That means moment at B, moment at C in the structure. So in the given problem, you don't have any applied moment at B, no moment is applied at B, no moment is applied at C. Hence, both the values are zeros. Okay, so it is 0, 0. Right? Next. Now, you need to find moment at B only due to the load and moment at C only the due to load only. Okay, so now for evaluating PL matrix, which means moment at B due to loads alone and moment at C due to loads alone. Okay, now you take fully restrained structure. Okay, which means the given continuous beam shall be fully restrained. Means you have rotation possible here. Now you restrain or restrict that. Rotation at C was possible. Now you restrict it. Okay. This is 12 meters. 12 meters. Now consider the loads. This is 40 kilonewton per meter UDL and eccentric point load of 120 kilonewton with 4 meters and 8 meters spans from either ends. Okay. Now you see AB is a fixed beam with UDL. BC is a fixed beam with eccentric point load. Now we are able to write fixed end moments MFAB, fixed end moment at A in AB. Okay, this is minus WL square by 12. Okay, so what is the value? Minus WL square by 12. You can just calculate the values. Okay, which is going to be minus 40 into 12 square by 12, which is minus 480 kilonewton meter. Similarly, fixed end moment at B in AB is plus WL square by 12 because this is going to be anti-clockwise, is going to be clockwise. So the same value but of sign change. Okay. Now let us write fixed end moments in BC. Okay, I'll write it here itself. Right. So MFBC value is negative anti-clockwise moment. P A B square by L square. Okay, so minus 120, A is 4, B is 8, 8 square by 12 square. So which works out to minus 213.33 kilonewton meter. Similarly for end C, fixed end moment, it is plus P A square B by L square, which means 120, 4 square, 8 by 12 square. So this will work out to 106.67 kilonewton meter. Okay, right. So what we want is total moment at B and total moment at C due to loads. This is what we require from this PL matrix. Okay, let us write it here itself. Right, moment at B you have two values. One is plus 480, this moment at B. Another one is minus 213.3. Okay, so let us calculate the total value. So that works out to this 480 minus 213.33. Moment at C is a single value, so 106.67. So this works out to 266.67, 106.67. So this is PL matrix. Okay, right. So once you are done with the P and PL matrix, now it is time to develop stiffness matrix and then further inverse of it. So as the Ki value is 2, we'll have 2 by 2 matrix. So now we are going to work out now these values utilizing the symmetry. Okay, we are going to work out only these three values because K21 will be equal to K12. Okay, so how you do that? So Kij, Kij. Okay, see that? So what is I and what is J in this one? So J refers to the displacement coordinate. Okay, I refers to force coordinate. It's just inverse of what you have learned, Fij, flexibility. Okay, so now what does this mean? You give unit displacement and calculate force required to get unit displacement. That will be your stiffness value. Okay, because stiffness from basic formula, it is P by delta. If you make delta is 1, that is displacement, if it is 1, then your P becomes K. P is equal to K. Okay, so which means give 1 unit displacement. Okay, and calculate force required to create this 1 unit displacement. Right, so this shall be done on the fully restrained structure. So now I take fully restrained structure. This is fixed. This is fixed. 12 meters. 12 meters. Okay. So now give 1 unit displacement at first coordinate. First coordinate is theta B. Okay. So this is coordinate B location. Just rotate it by 1 degree. okay, in the coordinate direction, 1 unit. Okay, so to rotate this fixed support by 1 unit, okay, how much is the moment required? That will be your stiffness value. So this is going to bend in this manner. Okay, right? So you have to apply moment at B in AB, again at B in BC to rotate this by 1 unit. So which means your K11 value, okay, will be of sum of two values, which is 4EI by L plus again 4EI by L. Okay, so this is our K11 value. Here also you need moment, you have the moment developed at C, okay, because you have applied moment at B, so you have carryover of half of the moment, that is 2EI by L. Okay, so this will be your K21, okay, which will be equal to K12 also, right? So this works out to 8EI by 12, and this works out to EI by 6. So this is going to be 2 4s are 2 6 are and 2 2s are 2 3s are. So 2EI by 3 is this value and EI by 6 is this value. Right. So going to find the other value of stiffness coefficient. Now you need to give rotation, 1 unit rotation at the other coordinate, that is second coordinate is theta c. Now it will be given 1 unit displacement. So rotate this by 1 unit. So if you say this is 1 unit, okay, how the beam is going to bend. So this is going to bend in this manner. Okay, so to rotate this by 1 unit, I need some moment, that is called K22 value. It is again 4EI by L, that is 4EI by 12, which is equal to EI by 3. Okay, so as we have EI by 3, here EI by 6 to EI by 3. So to have a common parameter to take it out from the matrix K, let us see. So first write 2EI by 3, EI by 6, EI by 6, then EI by 3. So if I want EI by 6 to be taken out from the matrix, I need to multiply and divide it by 2. So I'll have 4 here. Okay, EI by 6 is outside. So here 1 remains. 1 remains. Same here. So I need to do 2 by 2. So 2 remains here. Okay. So this is your K matrix. Now we need K inverse matrix. Let us find that. So K inverse is inverse of this 6 by EI, 1 by inverse of this 2 by 2 matrix. 4 2s are 8 minus 1. 4 1 I need to write 2 here, minus 1 4. Okay, so it is finally inverse of this matrix is going to be 6 by 7 EI 2 minus 1 4. So this is our K inverse. Okay, now substituting all these into the equilibrium equations that we have written earlier. So theta B, theta C, if I want, I need K inverse 6 by 7 EI 2 minus 1 4, and P matrix is 0 minus PL matrix is 266.67 and 106.67. Okay, now simplifying this further, 6 by 7 EI 2 minus 1 4 minus 266, 0 minus 266.67, 0 minus 106.67. Okay, now multiplying these two matrices will give you these two values. Let us say I want theta B value to be found. So I'll do 6 by 7 EI row column multiplication 2 times minus 266.67 plus minus 1 into minus 106.67. So this will give me minus 365.72 by EI. So this is your theta B value. Similarly, writing theta C 6 by 7 EI minus 1 times minus 266.67 plus 4 times minus 106.67. So we'll give you minus 137.15 by EI. So these are the two unknown displacements that we have identified in the structure as degrees of freedom in the very start of the problem. Right. Okay, you know the unknown displacements now. How to evaluate the end moments? That is what is finally required to draw BMD and to continue for SFD. All that you can do it only by calculating end moments. So final end moments are calculated based on slope deflection equations only. Okay, so use slope deflection equations. So I need moment at A. So I write slope deflection equation. MAB is MFAB plus 2 EI by L 2 theta A plus theta B minus 3 delta by L. So where there is no settlement given in the problem, so this term will be 0, and A is a fixed support, so this term will be 0. So we have already calculated fixed end moment at A, that is minus 480 plus 2 EI by length of AB is 12 into theta B. Theta B is just solved, minus 365.72 72 by EI. So EI gets cancelled. Upon simplification, you get a value 540 minus 0.95 kilonewton meter. So if you have seen the earlier flexibility matrix method solution, you can compare this answer that we have got now. It will be very similar and exactly same value with what matching with the earlier solution that we got from flexibility matrix. So similarly, MBA we can calculate MFBA plus 2EI by L theta A plus 2 theta B minus 3 delta by L. So this is 0, no settlement. This is fixed support. So A is 0, theta A is 0. Writing this plus 480 2EI by 12 2 times theta B minus 365.72 by EI. So which will work out to 358.1 kilonewton meter. Similarly, for member BC also, you can same way continue MBC value, writing the equation. So finally, you will arrive at minus 358.1 kilonewton meter. Similarly, MCB by writing slope deflection equation, if you continue, you get 0 kilonewton meter because end C is hinge in the given problem. Okay, so this is how you are able to solve, and you can very well visualize the video that I have made on flexibility matrix method to plot BMD, which is very much similar to the problem that we have already solved from flexibility matrix method. Okay, right. Okay, thank you.